Welcome friend in the next lecture of calculus first. In the previous lecture we discussed a squeeze theorem and some example on the squeeze theorem. In the today's lecture we have to discuss the monotone sequence and monotone convergence theorem. So we start our topic monotone sequence. First we discuss the definition of monotone sequence, then we take some example and then we go for the theorem. So first our topic, that is the monotone sequence. First we write the definition. Let x is equal to xn be a sequence of real numbers. Then we write the first definition. The sequence x is increasing if it satisfy the inequality that is x1 is less than or equal to, x2 is less than or equal to, x3 is less than or equal to, and so on. Xn is less than or equal to xn plus 1 and dot dot. So first what we write, x be the sequence of real number and it is increasing if first term is less than or equal to, second term is less than or equal to, third term and so on. Xn is less than or equal to xn plus 1. Similarly we write second definition. The sequence x is decreasing if it satisfy the inequality. Just you have to take the converse of this, that is x1 is greater than or equal to, x2 is greater than or equal to, x3 and so on. Xn is greater than or equal to xn plus 1 and dot dot. Okay. Third definition we have to take, that is the sequence x is equal to xn, that is the x is monotone if it is either increasing or decreasing. That is, we say that any sequence or the sequence x is increasing or it is increasing if x1 less than or equal to, x2 less than or equal to, x3 is less than or equal to, xn and so on. If it is decreasing, then this inequality will reverse, that is x1 greater than or equal to, x2 greater than or equal to, x3 and so on. And it is monotone, then it is either increasing or decreasing. That is the sequence which is increasing or decreasing. Then we say that this sequence is a monotone sequence. We see some example. First we write the examples of increasing sequence. Increasing sequence is a monotone sequence. Therefore they are the example of also monotone sequences. Here first we can write, suppose we take sequence 1, 2, 3 and dot dot. So what here, 1 is less than or equal to, 2 is less than or equal to, 3 is less than or equal to 4 and so on. That means this inequality is holds and therefore we say that the sequence x is, that is this sequence is increasing sequence. Second example, if you are taking 1 is 1, 2, 2, 3, 3, 3, and we can write dot dot. Now what you can say about this? 1 is less than or equal to 2, which is less than or equal to. Equal is sign, so the term may be equal. Therefore, this is less than or equal to this. Therefore, 2 less than or equal to 3. Again, it satisfies the first definition. Therefore, it is a increasing sequence. It is a increasing. Next is what? Third example. Suppose we write a square, a cube, and so on. But here we must need a greater than 1. That is, if a greater than 1, then we can write 1 square. That is, you can take any numbers. A is equal to 2, a is equal to 3, a is equal to 4. But if you take a is equal to 0.5, then what can happen? Think about this. Okay. If a is greater than 1, then this is definitely the increasing sequence. Now we write some examples. Examples second, that is the examples of decreasing sequence. Decreasing sequence. So first we write, suppose we take example 1, 1 upon 2, 1 upon 3, 1 upon 4. That is the reciprocal of natural numbers. Then this sequence is decreasing. That is, 1 is less than, greater than or equal to half is greater than or equal to 1 by 3 is greater than or equal to 1 by 4. So this sequence must be decreasing sequence. Suppose we take second example, that is 1, then 1 upon 2 square, 1 upon 3 square, and so on. Then this is again a decreasing sequence which satisfies the second property. Third, similar example we can take this, that is b square, b cube, and dot dot. But we are taking here 0 less than x, b is less than 1. Now take this b, it is in between 0 to 1. It is in between 0 to 1, then this sequence will be what? You can say decreasing. If we take b is equal to 1 upon 2, then what we are getting here? 1 upon 2 square is 1 by 4, 1 by 2 cube is 1 by 8, then 1 by 16, and so on. And if you see this sequence, which sequence is? This sequence is decreasing sequence. Is it? Now these are some examples of increasing and decreasing sequence. Now we take examples of sequences which are not monotone. That is, we write some examples of a sequences which are not monotone. That means which is not increasing or not decreasing sequence. Not increasing and not decreasing sequence. Here suppose we write a first example. That is, we write here plus 1, then minus 1, then plus 1, then minus 1. And this is the sequence, oscillatory sequence we can say. It is minus 1 raised to n plus 1. And this sequence, if you see, this sequence doesn't hold both the properties or one of the property from definition, and therefore we can say that this sequence is neither increasing nor decreasing. It is oscillatory sequence, and therefore it is not a monotone sequence. Similarly, you can take here any number, that is, you can take 2, replace 1 by 2, then you are getting again a alternating or oscillatory sequence. Again, you can write some definition like 1, minus 2, then 3, minus 4, 5, minus 6, 5, 6, and dot dot. This sequence you again see, this sequence is not a what? Decreasing or increasing, therefore it is not a monotone sequence. So getting this? So this is the very important topic. Now we will go for the monotone convergence theorem. We prove monotone convergence theorem. So our theorem, and this theorem is very important, monotone convergence theorem. Question may be asked for 4 or 6 mark or 5 marks, that is state and prove monotone convergence theorem. So it is very important, try to memorize this. So first we write the statement. A monotone sequence of real numbers is convergent monotone sequence of a real number is convergent if and only if it is bounded. That is, if we have monotone sequence of real numbers, this sequence is convergent if and only if it is bounded. Further, or we can write, if x is equal to xn is monotone increasing sequence, then limit of x as n tends to infinity, this should be what? Supremum of the set xn where n belongs to the natural number. Second, we can write, if y is equal to yn is monotone decreasing, then this limit as n tends to infinity of y, this must be infimum of yn where n belongs to the natural. That means what we have given, this monotone sequence of real number is given. What we have to prove, this sequence is convergent. Then we have to prove it is bounded. Again, we have to consider, here we have given if and only if. That the reason we have two parts, that is convergent if and only if bounded. So we prove convergent to bounded and bounded to convergent. So we have to prove this, and furthermore we have to prove this too. That is, if it is increasing sequence, this sequence converges to the supremum. Already we discussed what is supremum. If this sequence is decreasing sequence, then this sequence must converge to the infimum. So we write the proof. So what we have given? We have given that x is equal to xn is monotone sequence. It is monotone sequence. So we prove first part. That is, let x is equal to xn is monotone convergent sequence. So first we consider it is convergent sequence, and we know that. So we proved already one theorem. What theorem? Every convergent sequence is bounded. Every convergent sequence is bounded. Already we proved this, and this theorem is again very important. Therefore what we can write? X is equal to xn is convergent. Hence it is bounded. Okay, so this is our first part. It is convergent. We proved it is a bounded by using the theorem. So first part is completed. Now we have to prove the part second. So what is part second? We have to consider the monotone sequence which is bounded. Let x is equal to xn is monotone bounded sequence. What we have to prove? What do we have to prove? X is equal to xn is convergent. What is meant by convergent again? Convergent means what? The limit of the sequence is exists. So what we have given? We have x is equal to xn is monotone sequence. So what is meant by monotone sequence again? Monotone means what? Hence what we can say that it is monotone, then it is either hence x is either increasing or decreasing. Okay. Therefore what we can say that x is either increasing or decreasing. So again there is a two parts, that is we are written here already. So what? Let x is equal to xn is increasing bounded sequence. Is it increasing and bounded? Bounded already given. So it is increasing, it is bounded. So write down the definition, bounded sequence. So what we can write? There exists a real number m such that what? Mod of xn is less than or equal to m for all n belongs to the natural. That is just we write the definition of a bounded sequence. Bounded means what? All the term xn are less than or equal to m. This m belongs to the R. M belongs to the R. So what we can write? Therefore, according to completeness property of R. So according to the completeness property of R means what? This is bounded sequence. This is bounded sequence, therefore its supremum is exists. Therefore its supremum is exist. And suppose what we can say, x star is equal to supremum of all xn, n belongs to the natural number. That means what? We use the completeness property, therefore this sequence is bounded sequence. Hence what we can say that it is what? Its supremum is exist, and this supremum we assume this supremum is x. And now our claim is, what is our claim here? This limit n tends to infinity, x is equal to the x star, that is supremum of x. Now this is our target. So how we prove this? Again we have to use the definition. For every epsilon greater than 0, what we can write? X star minus epsilon is not an upper bound or supremum, or we can write supremum. Hence Hence what we can say, there exists a number xk in set xn, n belongs to the natural number, such that what we can write, such that what, this x star minus epsilon is less than xk. But what we have given, but x is equal to xn is what? Increasing sequence. And therefore what we can write, for this xk is less than or equal to xn for all n is greater than or equal to k. For all n is greater than or equal to k. This combined to this, what we can write, x star minus epsilon is less than xk, which is less than or equal to what? Xn, and all these xn are less than or equal to what? Our supremum, that is x star, and this x star must be less than or equal to what? X star plus epsilon. Is it? So what we can just, we combine these two, then all xk less than xn, we write this first, then here, but x star is supremum, means all the terms in this set are less than or equal to x star, and if you add epsilon, then this x star plus epsilon must be less than, that is, this must greater than x star. And if you remove the some terms, so that we can write x star minus epsilon is less than, it is less than what? This is less than xn, it is strictly less than x star plus epsilon. Is it? Implies that minus epsilon is less than xn minus x star is less than epsilon. And what we can write from this can be written, it is in the form of xn minus x star is less than epsilon for all n is greater than or equal to k. This is holds for all n is greater than or equal to k, and this is just the definition of a limit. This is nothing but our definition of a limit. Which limit? Limit x is equal to xn. Therefore what we can write from this? Therefore x is equal to, therefore limit n tends to infinity, x is equal to what? X star. And what is it? This is nothing but our supremum of xn, where n belongs to the natural number. Okay? So just we prove this, and therefore what we can cite, this is limit is equal to this, therefore the sequence is convergent. Therefore the sequence x is equal to xn is convergent sequence. Similarly, we have to prove the second part, that is the part B. How we prove this? We are not going all these steps. We have to use this part to prove the second part. Okay. So how we use this? Now let y is equal to yn is monotone decreasing sequence. It is the monotone decreasing sequence. Then what we can write? Then x is equal to minus y. X is equal to minus y. This is nothing but minus yn is. This is nothing but what? Just we take negative of this sequence, then what we can get? This decreasing sequence becomes a increasing increasing sequence. This is increasing. Therefore, from the part first, what we can write from part first. So what we can get, limit n tends to infinity, x is equal to, what we are getting here? Here nothing but what? Supremum of what? Here xn, but here we have a minus yn, all n belongs to the natural number. Okay, all n belongs to the natural number. Now what we have to use? Again, we have to prove the limit of yn is a infimum. Limit of yn is a infimum. That limit n tends to infinity, x is equal to minus limit n tends to infinity y. But what is limit of this? Therefore, what we can write, limit n tends to infinity y, it is equal to minus limit n tends to infinity x, and it is equal to minus supremum of all minus yn, such that what? N belongs to the natural number, and it should be what? Infimum of all yn, n belongs to the natural number. N belongs to the natural number. Therefore, limit n tends to infinity, y is equal to infimum of all yn, n belongs to natural number. And these things already we proved, it is in the first chapter. It is in the first chapter. Okay, and therefore we can say monotone decreasing sequence is convergent, and it is convergent to the infimum. It is convergent to the infimum, and hence from part A and part B we can say that a monotone bounded sequence is convergent. So this is the completion of part second. Okay, so it is very important theorem. So try to memorize this. In the next lecture we take some example on this theorem, monotone convergence theorem. So we will stop. Thank you.